Hello students, today we will solve a problem based on the application of Gauss's law. So the problem is, an early model for an atom considered it to have a positively charged point nucleus of the charge Ze, surrounded by a uniform density of negatively charged up to a radius of capital R. The atom as a whole is neutral. For this model, what is the electric field at a distance R from the nucleus? The question actually is telling us our positive charge is confined in the nucleus and that positive charge is equal to Ze, whereas our electrons are spread up to a distance of capital R. So this capital R gives us a spherical symmetry of the charge distribution, because the question says around the nucleus, which is positive in nature, our electrons are distributed up to a distance of capital R in all the possible direction or uniformly. So it gives us spherical the spherical distribution of electrons. Now this spherical distribution of electrons have same charge as that of the nucleus. How can we conclude that these electrons which are in this area have the same charge? Because in a statement they have mentioned that our atom as a whole is electrically neutral. This atom as a whole is electrically neutral. Neutral implies positive charge in the atom and the negative charge in the atom are equal. Positive charge in atom equals to negative charge in atom. That's why it is neutral. Now what they are asking us, that we need to find field at a distance small r from the nucleus. That small r can be smaller than our radius, can be smaller than capital R, or can be greater than capital R, or can be equal to capital R. We have three possible cases to undertake and to understand, like if our small r is smaller than capital R, what will be the electric field? If small r is greater than capital R, what will be the electric field? And when both the r's are equal, what will be the electric field? So let's moving on to the solution. Positively charged point nucleus of charge Ze, radius of the atom capital R, atom as a whole neutral. So total negative charge in the uniform spherical charge distribution of radius capital R must be minus Ze. Why we have taken minus? See, plus Ze due to protons, and then plus of minus Ze due to electrons. Now we have Ze minus Ze, it gives us 0, which gives us neutrality. Neutral feature of atom as given in problem. Okay, that's how we are concluding that the charge on the electron is minus Ze, since the atom is neutral. Therefore negative charge density is given as, how the charge density we can find? What is the formula of finding a density? density equals to mass upon volume. Okay, and this is our volume and this is our density. This is our volume of the sphere and it is equal to minus ZE. This ZE gives us the mass. Okay, we are equating these two things. Mass equals to rho into volume. So these are equal to, this whole mass is equal to ZE, and from here we are able to find the density, charge density of our atom, of our given atom, which is given as rho equals to minus of 3 ZE upon 4 pi capital R cube. Always and always check which kind of R they have used. Whenever we have similar variable, one in caps and other one in small, we make mistake by not observing which R we are mentioning. Here the density of the atom is given by this formula, where we have taken the radius of the atom, radius of the given atom. Now using Gauss's law of law to find the electric field at a point P. The point P, which can be anywhere. This is our sphere, this is the center of the sphere, and from here this is capital R. Point P can be here, one case. Another case, point P can be here, and the third case, point P can be here. Now what is the difference between these 3 point P's? That this is inside the sphere, outside the sphere, on the surface of sphere. R smaller, R greater, R equal to capital R. Because the spherical symmetry of charge distribution, magnitude of electric field ER depends only on radial distance and not on the direction of R. R can be in any direction, here, 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 anywhere in the sphere. Because it is radial and it is spherical in nature, just observe a ball. Ball have the equal from the center in any direction. If you see up, down, left, right, in any direction, ball have equal distance from the center. So same happen in the spherical distribution. So we are having same distance, so there is no need of mentioning the direction. No need to mention the direction, we can just take the radial distance. Now first case we have taken as R is smaller than capital R, that is R is inside our spherical distribution. So the electric flux enclosed by the spherical surface is given by electric field lines into the area. We know flux equals to E into E dot del S, right? So E of R into 4 pi R square, where ER is the magnitude of electric field at R, at small r, not at the surface. Okay, this is because on Gaussian surface at every point the direction of electric field is normal to the surface and have same magnitude at all the points. Now the charge Q enclosed by the spherical Gaussian surface, is given by positive charge at the center plus negative charge within the sphere of radius r. So we are taking charge inside, Q inside, and Q inside, which is positive, inside the nucleus, and Q outside the nucleus, which is negative. We are taking both the charges. Summation of these two charges will give us the total charge. So Q equals to ZE plus 4 pi epsilon naught R cube, small r cube, into rho, density of the whole. So here we have taken small r. We are defining the charge only for the sphere which is made by the small r radius. Okay, here we are defining only for small r. Don't get confused here that why we are writing this formula. We are writing this formula because it includes nucleus. This is our this, okay, from here R, from here capital R. So this one is having charge Ze, and this one will have charge density into this whole area, or the whole volume. We will not take area because it is a three-dimensional structure. We will consider volume of sphere. Okay, so volume of sphere into the density. That's how the charge we are finding. So Ze plus 4 pi r cube into rho. From our previous equation, from the previous slide, we know the value of rho, that is 3Ze upon 4 pi capital R cube. We will substitute this value here. And Q will be Ze plus 4 pi R cube, small r cube, minus 3Ze by 4 pi capital R cube. And we will take out all the commons, and for the Q we will get Ze equals to 1 minus small r cube divided by capital R cube. That is when point P is inside the spherical distribution. When point P is inside the spherical distribution. Okay. So now by Gauss's law, what we know is that E into area, electric field into area, is 1 by epsilon naught times the charge contained by the sphere. This is the relation of this flux. Okay, flux is given by Q upon epsilon naught, as well as flux is given by E dot del S. So we are comparing this equation with this equation. We are comparing both the equation of flux with each other. Okay, see here. Now ER, we have to find what? Electric fields, right? Electric fields. So redistributing this equation, we aim to find this. This is the question mark over here. Need to find this, redistributing Q by epsilon naught from here, 4 pi from here, and R square from here. This is how we are getting this equation. And now we will substitute whatever value we are having. What value we are basically having? We are having the value of charge inside this distribution. Okay, charge Q. We know the value of charge Q, which is given by Ze 1 minus small r cube by cap r cube. So we will substitute this value, and by redistributing and solving it further, we will get this Ze by 4 pi epsilon naught into 1 by r square minus r by r cube. How this is coming? I will solve it for you here. Just see, we get Ze by 4 pi epsilon naught r square into 1 minus r cube by r cube, that is capital R. Okay? So this is the value of E. Now we will take in common Ze by 4 pi epsilon naught, and this r we will try to insert it here. Okay, it will be r square minus r cube by r cube into r square. This r square will cancel this r cube, and only r will be left here. And hence E will be equals to Ze by 4 pi epsilon naught into 1 minus r square, 1 by r square minus r upon r cube. So that's how we are getting this equation. Okay, I hope you understood the derivation. And this is directed radially outward from this surface. These electric field lines are like directed like this, the way I am showing in the figure, radially outward. These are said radially outward from all the directions. How we can find the radius of a sphere in any direction, right? According to that they are distributed. Now we are moving to the case number 2, where R is greater than capital R. How that is seen in a pictorial way. This is our nucleus and this is our capital R radius, and our small r is over here, okay, outside the sphere. At this point, this will make again a spherical Gaussian surface on which we need to find the electric field lines. At point Q, we are taking this outside point as Q. Inside we have taken it as P. Outside we will take it as Q. The charge enclosed by the Gaussian surface is 0 because charge is present till here. There is no charge here. Okay, so charge present is 0 since the atom is electrically neutral. Like atom is electrically neutral, charge inside the nucleus is equal to the charge present up to the R range, up to the capital R range. But now we are coming out of our atom. So here the charge is 0. Outside the atom charge is 0. So from the Gauss's law, E of R into the surface area 4 pi r square, if we take, it will come to be 0. So in this particular surface area, the Q is 0. This is equal to Q upon epsilon naught, right? Q is 0. So this whole system will become 0. So if this system is 0, ER will also turn out to be 0. Electric field at this surface will turn out as 0. Similarly, at small r equals to capital R, electric field will be 0. Why so? Because when we are considering this spherical surface where capital R is equal to the small r, here also these lines which are going from here will come up to this point. Charge is enclosed till this point and this is electrically neutral. So it will give us 0 electric fields. But why can't we say that this sphere is electrically neutral when we have taken this much of radius? Because this charge plus this charge plus this charge, all these three charges, when we summed up, then only our atom becomes electrically neutral. But when we take only this charge and this charge, this is left out, right? This charge is left out, then how will it become electrically neutral? So when R is inside the sphere, we cannot say that it is electrically neutral. But when R is on the surface and outside the surface, we can say our atom is electrically neutral and hence the electric fields are 0 at that point. Okay, so that's the question. Hope you understood this last concept, why we have taken R smaller than capital R as some value. We have defined some value for this case, but for R equals to R and R greater than R, we said ER 0. Why we have said so, I think you have understood. In case for the clarity, I'll just tell you one more thing. See, this is our surface, one surface. On this surface, this particular point is having some value of 10, some 10 units. Now this whole value is having some minus 10 units of value, Now this is divided into another one part. So this part, this inside part is having units of 6, minus 6, and the outer part, this outer part is having some units of minus 4. When we are only considering the yellow and the blue, yellow plus blue, what will be the units we will get? It will be 10 for yellow, and for the blue it is minus 6. We will left out with 4. Now if we consider yellow plus blue plus red, what is the value? 10 minus 6 minus 4. It is equals to 0. So Here it is electrically neutral. When we covered the whole surface, it is electrically neutral. But when we covered the half surface, we found out that it's not electrically neutral. This is the thing, this is the concept we have used in this question to find out the electric field at various points. So it is very much important, always and always remember, inside a spherical charge distribution we will get some electric field, but due to the surface and outside there will not be production of any electric field. The reason is justified in this question. Okay, so we'll meet in the next class. That's all for today's class. Have a good day. Bye bye.